Okay, I think we're stabilizing. The audience is stabilizing, so maybe we'll begin slowly. So this is, as I said before, our main interest in this course will be on equivariant elliptic homology. I think it's what equivariant elliptic homology is best explained by explaining two related things, namely its little sister, equivariant K-theory, and the mother of this whole family, equivariant G-bordism. And so today we have the best person in the world to talk about this whole family. It's our very own Igor Кричевер, and so he will take over from here.
Okay, thank you for introduction. But I have to say that it needs a certain clarification. Of course, I'm not an expert in the field, because expert is supposed to present a state of the art, what is going on today. I'm here maybe rather as a witness and participant of early days of the equivariant G-bordism theory. So in certain sense, what I will present today is how it looked like about 40, 50 years ago. But maybe it's a good point to start making it more modern. So the first part of the lecture, I will try to explain how to one possible way of looking on a chain of cosmology theory. Andrei already told about equivariant cosmology, K-theory, elliptic, unitary. So if you go from top to the bottom, each time it seems the theory is complicated, and in certain senses it's not clear how to proceed. My point of view is to present some view when it's easier, much easier to go from bottom to top, seeing elliptic cosmology, K-theory, usual cosmology as certain evaluation of a mother theory, and why its unitary G-bordism theory is mother. This is another goal of my talk, to explain why. So generally, cosmology, in old days it was called extraordinary cosmology theory. It's any theory that is a functor from the category of pairs of topological spaces, to be on safe side. It's always good to have in mind CW complexes, whatever it means, to some abelian category, with standard axioms of Eilenberg-Steenrod, all that are listed here: functoriality, homotopy, long-exact sequence, excision axiom, disjoint unit, all but last axiom about region of coefficients. In ordinary cosmology, we have that all cosmology of a point with n bigger than 0 are vanishing. That's not true for cosmology, cosmology theory. And
Igor, we can't see if you're sharing your screen. I don't think we can see it.
Oh, let me just. You don't. Sorry. Can you see it now? Andrei, can you see it now?
Much better, yes.
It's easy to be better than 0, as always. Okay, so, and we will talk about, first of all, about multiplicative cosmology theory, and more, some nice theories which are well for a notion of a complex vector bundle. So nice theory. So by nice theory, I mean a theory in which a notion of Chern classes for complex vector bundles exists. And for that, you need to require that complex vector bundles are H, it's called H orientable. And that means that actually, in fact, what I need the so-called Thom isomorphism that tells that if Xi is a vector bundle over some space, vector bundle, complex, let me not mention every time. So whenever I'll speak about vector bundle, it will be a complex vector bundle of complex dimension n. Then there exists an isomorphism between cohomologies of the space, the base, and the cohomologies of the pair consisting of d of psi is a vibration by disks, unit disk, you can introduce some matrix, and spheres. So this is isomorphism, and it is defined by the so-called Thom class, which is a class in the cohomologies of the pair, DS. And this isomorphism is just a multiplication by the, so it's into and this isomorphism is multiplication by Thom's class. This is what is easily to be established in many theories. It's known for K theory, it's known for cobordism theory, unitary cobordism theory we will be talking about. And an easy corollary of the existence, which I also will use later on. And actually, this is the most essential part of all localization theorems existing in the theory, which we will talk about later, is the existence of this Thom class and the fact that if you include X in B by zero section in B, then the image under induced map of Thom class is just the Euler characteristic of a bundle. And as a result of this isomorphism, this is so-called Gysin exact sequence valid for all vector bundles if they are H orientable, and this is H star minus 2n of X going to H of X is multiplication by the Euler class, and then H to the sphere bundle and delta, which goes to H star minus 2n plus 1 of This is sequences used to derive the localization theory later. So, but it also can be used, and again, it's crucial for all other consideration, is that from that sequence, it's easy to derive that cohomology of the projective space, complex projective space, is isomorphic to the Taylor's formal series in some variable u, which is exactly earlier class of the canonical bundle. It's canonical bundle. Canonical line bundle. Canonical line bundle. That is present in any H-orientable period that is compatible with H-orientability of complex vector bundle. Usually, any theory should be completed, if you want to decide it in full generality. There is a Brown representation theory that actually says that a theory is uniquely defined by so-called spectrum. Spectrum is a sequence of spaces with maps between them, such that the suspension or wedge product of S1 with Mn is homotopy equivalent. There is a map from this to the next term in the spectrum. And then if you have a sequence of such spaces, then you define by this spectrum cohomology theory by taking the limit when k goes to infinity of homotopy classes of maps of wedge product of sk with x over a to mn plus k. And this is cohomology, and respectful homology theory is again the direct limit of sk plus n sphere to wedge product of xa wedge mk. So this is just homotopy definition of cohomology theories. Sometimes it's very hard. An example with elliptical cohomology shows that constructing a spectrum for elliptical cohomology is by any means is highly non-trivial task. It's hard to read even. And in many, from my pedestrian point of view, it looks rather like existence theorem. There exists a spectrum for such theorem than explicit construction. Too many relations you need to improve. We will discuss cohomology theories in much more simple way. But before I'll do that, I need some necessary facts from the theory of formal groups. Formal one-dimensional dimensional formal commutative group. So the notion of formal group is very simple. It's a series in two variables. So it is so K is a ring, and we can see the formal series in two variables with coefficients from some string. And this formal group law should satisfy certain properties. First, it should be U0 equals U. 2 is commutative, UV equals FVU. And the third property is associativity of this addition law. So F of U, V, W is F of U, F, V, W. These are three constraints for a series. The first and the second means that it starts with a U, V equals U plus V because plus some alpha ij, ui, vj, and I plus j should be bigger than 1. This is two axioms, and the associativity is a lot of relations on the coefficients of this formal series. I, j is in the ring. So before I'll say a few words about general theory of these formal groups, let me explain why we are interested in these formal groups in connection with cohomology theory, because formal group of cohomology theory can be defined whenever you have actually a first term class of line bound, namely by definition FH of UV is the first term class of a tensor product of two line bundles on two copies of CP infinity in projective space. So it is in the cohomologies of the product of two projective spaces. We saw already that the cohomology of CP infinity is formal series in the variable U, the other in the variable V. So taking the tensor product of two line bundles, so we take psi is a line bundle over one component, eta is the line bundle over another copy of CP infinity. We lift them by projection to the direct product of two projective spaces. We get two line bundles over the product of two projective spaces, take the tensor product. It has a Chern class. And that is a formal group law. And as we will see, surprisingly, this formal group law almost, and in many cases, completely defines the cohomology theory. So all cohomology theory is encoded in this formal group of the theory. Okay, just to explain what I mean, let me tell, but first, let me just give you a couple of examples. Of course, there is a simple example, is the usual addition, additive. It's just a sum. This is a formal group. It's additive. And this group is actually how Chern classes in ordinary cohomology theory behave. So the Chern classes of tensor product is a sum of Chern classes. Tensor product of two line bundles is a sum of Chern classes. This is one example. The second example is as Chern classes in K theory is called multiplicative group. It's U plus V plus UV. Multiplicative. This is again a formal group. You can check that this is indeed satisfies a surjectivity condition. And for today's purposes, I'll present also another, which is not so obvious. This is a formal group law. U radical of P of V plus V radical of P V U divided by 1 minus epsilon U square V square. We'll see later. This is elliptic of group law, where P is any polynomial of the fourth order 2 delta T squared plus epsilon T to the fourth. And the ring of coefficients of this elliptic formal group is just Z extended by 1/2 and polynomials of two independent variables, delta and epsilon. This is a family depending on delta and epsilon of formal group laws. We'll see some examples of formal groups later, but I would like to explain in a few minutes why, using these formal groups, why, to some extent, unitary cobordism is a mother theory of all other theories. And so for that, I need.
Sorry, should we understand this group law number 2 from the definition? Like you gave some construction about product of 2CP infinity.
No, I just, well, okay. First of all, there is a construction of formal group from the cohomology theory. This one thing that relates the first part with what I am talking about. The other is just a formal definition of a group law. And in this definition, it's just you can easily check that under the number 2 there is a the rules U plus V plus UV is a formal group associative. That's all. How to relate in K-theory. In K-theory, you have multiplication of tensor. Actually, the line bound by itself is, to some extent, is a Chern class. But you need to make it virtual, so you just take L minus 1, psi minus 1, tensor with multiply with eta minus 1, and you will get this multiplication.
Thank you.
This is just usual the rule of tensor multiplication of two virtual virtual line bundles. Okay.
Yeah, thank you very much.
Okay. So there is the mother theory in cohomologies is related to the fact that there is a mother theory or mother formal group. It was proved by Lazard without any connection to the cohomology theory. It's just a theory of formal group laws. He proved that there exists a universal formal group. So there exists a group F of UV over some ring K hat with coefficient such that for any F of UV, so for any formal group, there exists a homomorphism, let's call it F tilde, from the ring of this universal Lazar ring to the ring of your formal group, such that F of UV is F tilde, not a very good notations, F of UV. So, first of all, if you have a formal group and you apply homomorphism to all coefficients of this group, you will get a new formal group. It's obvious. The statement of Lazar that there exists a universal group such that any formal groups are classified by the homomorphism of this universal Lazar ring to the ring of your formal group. That is one piece of information. And the other is okay, actually, let me just tell how you can define such a group. Over Q, so if you tensor your ring by Q, all formal groups are isomorphic. What that means, that actually can recover F of UV in the form G inverse G of U plus G of V. So there exists a G, a formal series, lambda I, UI, such that after substitution, change of U by the formal series, it becomes linear. And universal Lazar formal group is defined as follows. The logarithm of this group has the form. Take the formal series xi over xn over n plus 1 u to the power I n plus 1 n from 0 to infinity xn independent variables. Compute the formal series f of uv by taking the inverse series, plugging into the formula, you get f of uv. Of course, over q, it is defined, it's a polynomial in x, in infinite number of variables. But take the smallest ring that contains coefficients of this formal group. And this is the universal Lazar ring. This is how, and you can, and then you can prove that any formal group is image under the some homomorphism of this universal Lazar group. So, and remarkable facts proven by Whelan based on, actually it was in some implicit form, it was already in the works of Mishchenko, Novikov, Shtaber, that formal group of unitary cobordism is the Lazar formal group. So actually there is a realization of this universal group in terms of the formal group associated with unitary cobordism theory. Okay. Actually, Mishchenko, he proved that the logarithm for unitary cobordism theory looks like it is supposed to be for the Lazar theorem, namely it's I from 0 to infinity, Cpn, it's a cobordism class of Cpn over n plus 1, u to the power n plus 1. Of course, there was a need to check that there are no more relations that so the ring of coefficients is not bigger than Lazar's ring, but that was completed by Quillen. But starting point was the formula for the logarithm of it's called geometric cobordism, a formal group of geometric cobordism. Okay, so I said that I will define in a minute the unitary cobordism, but let's first look what universality of the formal group of unitary cobordism means. It means the following, that for any theory, you start with any theory, cohomology theory, for which there exists a first term class for which you can assign a formal group law of this theory. And that means that there exists a homomorphism of the coefficients of the universal theory to the coefficients of this formal group because of Lazar's universality theorem. So there exists a homomorphism from the coefficient, from cohomologies of a point in universal unitary cobordisms to the coefficients of your theory. And when I said that in many cases you can recover from the formal group defines this homomorphism. Then we can define a theory X, Y. Yes. Okay, just by taking just a tensor product, XY, unitary cobordism, with H star of a point, and this tensor product over this homomorphism defines this tensor product. Clearly, tensoring one cohomology theory with some ring preserve all axiom of a theory except exactness of a long sequence. So if H is flat, is Van Weber, or Van Weber flat, it turns out that as two graded theories two graded means that you split grading in even and odd part and define a new theory. So in that sense, your initial theory is completely recovered by this simple formula. So you recover your theory by taking tensor product of the theory of unitary cobordism with coefficients. And all you need in this definition, just the homomorphism defined by the formula. For example, K theory is, or maybe it's too early to say, K theory, elliptic cohomology, are Van Weber flat. Sorry. Any questions? Okay, so this is one point of view. I mean, having a cohomology theory, you define the homomorphism of unitary cobordism into cohomology of a point. Now let's forget about the origin of this homomorphism, not a theory. Let's first try to define a theory starting from this point. For that, we need a way to construct or classify or look at what are homomorphisms of unitary cobordisms into any ring. So, or how to construct some homomorphism of a ring of cobordism. So we reverse the logic from the theory to formal group. Instead, I want from the formal group to define a theory. Okay. Any questions? Okay. So a brief account, what is unitary cobordism theory? It's easy to start with bordism, unitary bordisms. Okay, having X and A, we define omega of X, A in a very natural way. It's all maps from M, dm. M is a manifold with a boundary dm into X and A. Modular equivalence, Bord equivalence. And for two manifolds to be equivalent, Bord equivalent means so M n and M n tilde M n M n tilde. They're equivalent if they exist W n plus one dimensional manifold with a boundary such that Mn minus M tilde n. I'm saying minus because this is in case you can define actually bordism relation, refine the notion of bordism relation by putting in different structures. The original definition for non-oriented manifold was introduced by Tom. In that case, you just take просто the border is disjoint union of two manifolds. In orientable case, you need to take into account orientation. There is a whole bunch of theories: unitary, symplectic, special unitary, frame. So whenever you add some additional structure, refined structure on a manifold and maps, you get some variance of the theory. So we will consider unitary bordisms, XA, unitary bordisms. Bordisms with complex structure in a stable tangent bundle. By stable, I mean you just add some trivial bundle and introduce in a consistent way complex structure on a direct sum of your tangent bundle plus trivial bundle. This is the standard way to introduce unitary bordism. And that is simple theory. So, and we will be talking about stable unitary bordism. The ring of coefficients or the cobordism, bordism, unitary was computed by Milner and Novikov independently in 60 or 80, I don't remember. Okay, so and so the ring of coefficients, which is, by the way, the spectrum of unitary cobordism theory is very simple, easy to construct. Spectrum is a sequence of Thom spaces of standard of Thom spaces of universal UN bundle over BUN. The Thom space is what? You take a bundle, associated bundle of disks, and with a boundary spheres and factorized by spheres. So this is a Thom space of the universal UN bundle, and that they provide the spectrum for unitary cobordism. So Bordism of a point, they're canonically isomorphic to the cobordism of a point. And so we are in position to classify, to define all homomorphisms, because, as I said before, any theory defines homomorphism from the ring of coefficients of cobordism theory into the ring of coefficients of your theory. So how looks rational, tethering with the rational. So how looks the homomorphism to rational? So this is, I need to define Hirzebruch. Multiplicative genera. So any homomorphism from U star in bordism of a point, there is a natural multiplication. You just multiply, take a direct product of manifolds, and this is a product in this ring, which is isomorphic to the product in the homologies. So how to define homomorphism to rational numbers? Hirzebruch is defined in the following way. It is defined by h of x. So take any formal series, x plus some lambda I x to the power I. Sorry, I'm using the same letter h for a formal series and the same letter for the homology theories. This is with intention, because the homology theorem and formal group multiplicative homomorphism of unitary cobordism into rational, they're very closely related, defined one by the other. So that's why it's probably abuse of notation. But now H not a theory, it's just a formal theory. And this H induces homomorphism from P of T to the rational by very simple rule. You need to compute the value of this homomorphism onto some manifold. You take a product of the following expression, xi over h over xi, some symmetric combination of this formal series. So this starts with with one, that's why you can divide. So this is a well-defined Lorentz series, formal series in Xi, and Xi defined. So the symmetric. So this product can be expressed in terms of symmetric powers of Xi. So if we introduce Xi product equals 1 plus Ci, C1 plus C2, so on. So this is so-called Wood generator. Replace any corresponding symmetric combination of Xi by Chern classes, evaluate on the fundamental class of X, you get a number. It's a rational number. So all homomorphism from unitary cobordism to rational are defined by by formal in such a way, by formal. And that's called Hibbs-Brook multiplicative genera. So the relation of H with the logarithm of certain of a group, because if you have a homomorphism H hat here, you can apply this homomorphism to the universal formal group of geometric cobordism. You get a new formal group. So the logarithm of this new formal group is G of U is sum. So we take the formal group of the geometric cobordism, apply H to covariant classes of CPN, divide by n plus 1, U n plus 1. And this is the logarithm of a formal group of associated with H hat. And Novikov, it was observation by Novikov that H, which is a formal series here, is nothing but inverse series of G. So Novikov's observation. So this is general definition of rational Hibbs-Brook genera. All classical genera are obtained in this way. Later, maybe I'll talk a little bit about third genus. Signature of the manifold. A genus for spin manifolds. They're all examples. So third genus corresponds to the homomorphism under which CPN goes to 1. For signature, CP2N is 1, and signature of odd CP2N plus 1 is 0. Okay, so now we know how to construct or look at homomorphisms of the from the unitary cobordisms to rationals. Now I want to define, to a certain sense, the most general form a good, so generalized elliptic genus. So this is a genus, particular case of Hirzebruch multiplicative genus. As we know now, any genus is defined by one formal series, h of x, h of x. So you take any formal series, you get a multiplicative homomorphism. All classical genuses, including elliptic genus, which we will talk a minute later, are particular cases of a family. It's 4 parametric family of formal groups. And they are defined in the following way. I'm afraid my introduction to the equivariant cobordism is taking too long to have a hope to finish today, but so I define a function, the omega 1, omega 2. So it's a function explicitly written in terms of the classical sigma zeta Weierstrass function. So you have elliptic curve with periods 2 omega 1, 2 omega 2. With every elliptic curve, there is associated family of functions. Weierstrass function is antiderivative in zeta function, and further there is okay. It's like a Jacobi theta 3 function with some change in normalization. So let me write this function explicitly. X sigma of z e to the power of zeta of z x. Yes. So this is a formal series. This is a function. It's really elliptic function in z. So x z plus 2 omega alpha. Omega alpha is not any of the periods of your elliptic curve. So it's periodic. So it's indeed periodic. It's a function on the elliptic curve, z variable. But it's not an elliptic function because it contains a central singularity at 0, z equals 0. Z equals 0, essential singularity. As a function of the variable x, it is not an elliptic function, but it's a section of a line bundle, namely, it gets transformed under the shift x plus 2 omega alpha z skip. It is phi of x z times e to the power 2 zeta of z omega alpha minus 2 eta alpha z. So it's a section of a line bundle over elliptic curve. And if we take and expand it at z equals at x equals 0, phi of xz It starts with 1 over x plus some regular. This is Laurent expansion of this function at x near x equals 0. So we can define in this way the universal elliptic genus by just choosing the corresponding generating function x as 1 over phi of x z omega 1 omega 2 e to the power k x. So we have a family of formal series that depends on z, e, omega 1, and omega 2. And by definition, any such series defines a genus, and that is called generalized elliptic genus. We claim, I'm not going to check for all, in full generality, is all classical genera, including elliptic, particular cases of these generalized elliptic genus. Actually, I call it generalized elliptic genus, although it was known, at least for me, some others, long before the elliptic genus was introduced under the different, from the different perspectives. So this is a remarkable function that is, let me just draw it in a box. It's the simplest case of the so-called Baker-Ahieser function. So this function as a function of x and z satisfies the Lamé equation. The second derivative in x minus 2p of x. This is Weierstrass function applied to phi of x, z. I'll skip notation or dependence on pairs of elliptic curves. Is q of z phi. So it's eigenfunction of the Lamé operator. And it satisfies the remarkable addition type relation, which underlies the use of this function in many things in the theory of the elliptical Moser system, in some other things. So there is addition theorem. So phi of x plus y multiplied by p of y actually equals to the Wronskian p of x, p of y And this is identically z for any z, for any z. There is this addition form that expresses in implicit way the evaluation phi at x plus y in terms of phi of x and phi of y. Just some form of addition theorem for elliptic functions. And in addition, there is a relation phi of x times phi of minus x equals p of z minus p of x. So phi depends on x and z. X z minus x z. Okay, so it's easy exercise that if you take phi x and substitute evaluated at z equals 1 of the half period, so we have a family of formal groups depending on several parameters, z, periods of elliptic curve, but if we specify z to be 1 of the half periods, one gets elliptic formal group. Formal group is a particular case. All the classical groups like formal groups associated with thought genus, signature, A genus, corresponds to degeneration of this elliptic curve to a noodle rational curve. That is all well known in relation of elliptic Cauchy-Moser system with trigonometric and rational ones. So this is a kind of the most general nice genus. What I mean by nice, and it contains all other classical and elliptic as a particular case. To explain why it's the what is so remarkable about this generalized genus? I can finally explain it. I need to go, and that was the original goal of my talk, to speak about equivariant Bordism theory. To define equivariant Bordism theory is very simple. So you just definition. To define a group of equivariant Bordism of a manifold with an action, so G acts on X. Just consider the definition of Bordisms. So you're taking a maps of a manifold M into X, but equivariant. Most natural relation, but Bordism relation. So the definition of the groups is very nature. Of course, without having a spectrum to define a dual object, cobordism, it's harder. And I'm not going to To define it, reader, you see here. For me, okay, dealing with smooth manifolds and having in mind concurrent reality, cobordism are objects dual to bordism. But as a, so we'll talk and try to study these objects without explicit definition. But what one should expect to define such a thing? Of course, you expect that if X is a free G manifold, main manifold, then you should expect that if such a reasonable theory exists, then the cobordism of X should be equal to usual cobordisms of a factor space. So it's a manifold, not necessarily. This is one obvious requirement. There is some substitution of this definition when you can make from any manifold with G action homotopy equivalent manifold with G free action. So you have, so let X be space with an action of G on it. Then we define, it's called barrel construction. Then you can define an object which is a bundle of a universal classifying space, BG, of your group, by taking a product X with a EG, which is contractible space with a free action of G. So on this product, the action is GX freely, so you can take the factor space. And this is by definition XG. So you have a bundle of a BG with a further, which is X by itself. And the same, of course, the universal, the cohomology of classical unitary cohomology, as you can define the same for any cohomology theory of XG, they are not, of course, what we are looking for in definition. There's no K theory, the completion of equivariant K theory. But we'll see inside what many answers on question you may ask about manifolds with action of G. Andrei. Before explaining how looks the bordism of manifolds with action of S1, which is the prototype of what we would like to see about equivariant cobordism of connected leaves Lie groups. Let me define you some objects and then see the localization theorem for unitary cobordism, namely what I want to define. Suppose you have some characteristic class. Characteristic of a complex bundle, it's an element of cobordism of universal classifying space. So Chern classes, their combinations, they're all in cobordism of a unitary class. So we can define equivariant for each Chern class, characteristic class. And we define it in such a way. If psi is G vector bundle over X, then by Borel construction, we have a bundle psi X, psi G over XG. Just we take total space of psi multiply by EG, take a factor, and this is X times EG over G. So you have a bundle. So you can take psi, its value of COG, and take the push forward, and you get element in unitary cobordism of your classifying space BG. That we will call X characteristic class XG of G. This is by definition. So characteristic classes usually takes values in unit in homology of a space. Now we just define them for characteristic element as a result of pushing forward to the homology of DG. So, and from what I will need in what follows, a general notion of localization theorem, which tells you the following. Let H be a normal subgroup of G. Then and let Fs be fixed point, fixed submanifold. Connected components. Of fixed point set, fixed points set of of H actually. So we're taking not fixed points of G by itself, but picking any normal subgroup. We can take fixed points of H actually. Because it's a normal, they're invariant on the direction of G. Also, they're not fixed by G. And then there is the localization formula is the form. So if you take for any, in particular one, well, for any characteristic class psi of G, it's going as a sum over S or all connected components of PS push forward of evaluation of psi S G. So you just restrict your psi onto the submanifold Fs, divide by the normal bundle to this component, and that is well-known formula in, okay, this localization type formula is well-known in cosmology, in K-theory, in case when H is coincide with G. But in fact, it's, as you will see later, it's useful to write also in terms of for any H, for purposes that will be clear later. And it is true for unitary covariance theory. Okay. Andrei, okay, maybe someone can answer my question. Till what time do we have?
I think you have 6 more minutes.
6 more minutes.
But I'm not the organizer, so like you can have whatever you want.
Okay. I'll jump a little bit to be able to explain what I meant by saying that generalized elliptic genera is the most nice genus in the following sense. Okay. Equivariant group. Group. So, by that, so we already saw that if you have any multiplicative genus defines you a homomorphism from the ring of coefficients to rational. That can be extended to homomorphism of functors, namely U tilde X goes to A of X, tensoring with Q. So because by Dot theorem, if you have a homomorphism of coefficients, then there exists an extension. There is a homomorphism of theories. So for any Gibbs-Rule genera, there exists a homomorphism of the theories. Now we define equivariant genus of any G manifold with values in K of X with genus with K of a point tensor Q, just a ring of representation, by composing. So we take P of 1 in the Borel construction. So we get an element in cobordism of G bundle and defined to have its image would be living in P theory of a form. So the values of this equivalent, so the usual values of Hirzebruch genus are rational numbers. Now values are representations. It's called index character. Index genus. The sense of this genus is the following. The most classical genuses coincide with the index of certain elliptic operator on the manifold. Signature is the index of Laplace operator. A genus for spinors is the index of Dirac operator. So index character is, instead of taking the action of a, if everything is equivariant, then you have on a kernel and a kernel of your operator, you have a representation of G. You take the difference, you get an element of K of the ring of representation. This is a index character. So the value of, instead of signature, you have some element of a ring of representations. Of course, if G is connected, then the representation of your group, continuous group of in cohomologies with integer coefficient must be trivial. And that means that actually the index character is a constant. And that was called by Atiyah Hirzebruch rigidity property. And they actually they used this rigidity property to prove some remarkable relations. For example, that if you have S1 manifold, the signature of this manifold is a sum of signatures of the fixed point sets of the S1 action. That is obviously true for if you take Euler characteristics for signatures, it's a surprise. And that comes from the rigidity property. Actually, the whole story about elliptic cohomologies came from the attempt to prove the Witten conjecture that elliptic genus has a rigidity property for S1 action, and it was finally proved by because elliptic genus was realized as an index character of a Dirac-like operator on loop spaces, which is hard to make rigorous from the mathematical point of view. So let me just state the rigidity property of this generalized elliptic genus. And maybe that would be sufficient to make you interested in this subject. So for any H homomorphism from U star to Q, you define equivariant genus which takes values in K of B, G, tensoring with Q. Equivariant genus. H is rigid if image of HJ is in Q sitting inside K of BG, tensor Q for G and so this generalized elliptic genera is the genus having such a property, elliptic genus is rigid for SU. And the way to do so, this is the theory. And there is no, of course, any theorem that is the most general genus, but, and actually I don't know even how to attack this problem, but I believe I can check that is true. And that explains why all these theories, K theory, elliptic homology, are so special. They have this, they are defined by genus with this rigidity property. To give the idea how to prove it, I need to go through what I was planning to present, but was unable to do so because my time is running out. So once again, I just want to stress the points. Okay, in many cases, we don't know how to define a theory, or it is very hard to define a theory. The definition of elliptic homology is unbelievably complex. So as a good approximation, this is my point of view, instead of a theory, you just consider a pair. So for me, homology theory approximately, it's not exact method statement, it's unitary cobordism plus multiplicative hexaproof genus. And that is very tractable, and effectively you can compute all objects you need, just using only coordinates that are well-defined, easily computable, and genus, which is also computable. So, and as I said, the coming from cobordism to elliptic homology, K theory, usual homology, you realize that this theory I mentioned, they're defined by genus. with the rigidity of that's a summary of my today's lecture. Any questions?
Questions? Sorry, I couldn't participate in discussions earlier. I didn't have my microphone on, so.
Yes. So, Andrei, I was unable to present in today's lecture the middle part, how to describe S1 G-bordism of G-bordism. But probably it's there.
There may be a good point to come back to this later, because we will have to talk about rigidity later in some technical arguments, and maybe there'll be a good logical point to revisit the issue of rigidity later in the course. So we'll plan for that. Yeah. More questions? Well, if there's no more questions, let's all thank Igor very much for a wonderful lecture, and we'll see each other again in 1 week.
Okay, thank you.